So we're going to start talking about the Boltzmann distribution and thermal equilibrium. And I find it amazing that this simple equation is so accurate in describing thermal equilibrium. And it's everything from rotational equilibrium to vibrational equilibrium to two-level systems and bond association. I mean, it's throughout all of chemistry. It tells us really the definition of what we mean by thermal equilibrium. If something doesn't follow the Boltzmann distribution, we could say it doesn't follow it yet. Okay, so things are going to relax if they will relax to that Boltzmann distribution of states, and this ties into the probability chapter that we did last time, where there's really nothing special about any of the energy levels. Okay, and so it's just like musical chairs. The molecules and the atoms are jumping from level to level. It's constantly dynamic. One jumps down 2 levels and gives a photon to 2 other molecules, and they go up 1 level each, and so on. So there's constant change. And you learned that in Chem 2 when you were learning about equilibrium, how there's constant change. That equilibrium is really when the rates of the forward reaction and the reverse reaction are equal, okay, that you're at equilibrium. But really, nature doesn't know anything about reactions. Nature just knows about quantum states. And so whether a bond breaks or makes, those are just 2 different quantum levels. And so if it jumps to a level where there's no bond, then the system is on that energy level, in that state. And so it's constantly hopping up and down to all these different levels. And there's no categorization in nature that says, okay, you're a reactant, you're a product. They don't have labels. They just have energy states. And so if they're hopping from energy state to energy state, there may be a chance where they hop to a state where they're now the two species instead of one. Okay. Now, it may be hard for that to come back because those 2 species have to find each other and interact and maybe go through an activation barrier and find their way down to a lower energy state. But statistically, that might happen. And so then you have the reverse reaction. And so you have all of these reactions taking place based upon just like Einstein was resistant to. He says, I don't think God plays dice with the universe, but that's what appears to be the case, that these molecules are hopping around from energy level to energy level. As long as they have enough thermal energy in the system, they have more access to the different levels. So let's talk about those energy levels, and that's what we'll do with the Boltzmann distribution. So the probability of a particle, okay, screen, how about that? Okay. Let's see, do I have the right? I think I'm using the handout. I want to use the, let's see. No, I got the right one. Okay. Okay, so I must have messed up. But it's the probability of a particle being in any given state, okay, is given by this Boltzmann distribution function. And you can see that this piece up here, this piece here, right here, is what we call the Boltzmann factor. And it has this piece out front, which is the degeneracy. And that's the degeneracy of a given level. So we indicate those levels with the index I. And so each little I is a different energy level. And so think of the degeneracy. I use the example you're familiar with for the longest in your chemistry career. That's the s,p,d,f orbitals. And so P has a degeneracy of 3 and D of 5 and F of 7. And so that's an energy level, the p orbitals, but there's 3 of them there. So we put a 3 in front to take into account that there's 3 chairs on that level. And then the d orbital, there's 5 chairs. And so if this is like musical chairs, there's 5 places to sit in the d orbital energy. And then we have the energies of those individual states right here. So that's the energy of the given state that we're talking about. And then this is the temperature effect. I like to call this the thermal bath. Because I like to think of it, it's sort of the level of the water in the bathtub. Okay, you have a certain amount of energy in the system, and that can be distributed among all of the individual energy levels. Okay. Now we have Planck's constant, or I mean Boltzmann's constant here, 1.38 times 10 to the negative 23rd. The degeneracy is GI, the energy is EI, and the temperature is T, and it's always in Kelvin. Always, always, always. Now there's a lot of times we're dealing with spectroscopic systems. So we're dealing with rotational energies or vibrational energies, and those happen to be in wave numbers. And it's a real pain to do this whole thing in joules, because you're converting wave numbers over into joules and using Planck's constant. You have all these factors, 10 to the minus 23 and everything, and it's you have tons of scientific notation, whereas you could just convert Boltzmann's constant over to wave numbers by dividing it by h and c. So if you take Boltzmann's constant and divide it by Planck's constant and the speed of light in centimeters per second, then you end up with this nice clean number here, 0.695 wave numbers per Kelvin. So that's just Boltzmann's constant written in different units. And so if you have a system that has, let's say a vibrational energy, we did the last lab we did last fall was the iodine lab, and the vibrational energy for iodine was 214 wave numbers. And so that's really convenient if we have up here this energy as 2, 1, and 4 wave numbers. Then we can have Boltzmann's constant 0.695, and if we wanted to do room temperature, say 300 Kelvin, all of those are nice numbers, right? And so it's sometimes helpful to use Boltzmann's constant in wave numbers. So you don't have to do the whole thing in joules. You can convert the units to whatever you want. Okay, so if you get units of wave numbers in energy, go ahead and convert Boltzmann's constant over to wave numbers so that everything is nice and neat. Okay. It'll work either way, but I like to use it this way. Okay, now let's talk about this denominator here. Remember, the probability is the event over the total number of events, right? That was from the last chapter. And so the total number of events is just the sum of all of those Boltzmann factors. Okay, that's what we call the normalization, or another term for that is partitioning. And so let's go back to the last problem that we did in the last set of notes. We had this dartboard, and we throw darts at the board, and then we have 3 areas where they can go. And the rings around those areas are partitions. Right? You ever come into a room that has temporary walls? They put up these partitions to kind of break the room into smaller groups. Okay, that's what's going on here. We have this dartboard, and we've put up walls to break it into smaller groups. We have a red area, a blue area, and a green area. And those walls are partitions. So this denominator, if you'll notice, is the sum of all of the partitions. See that? And so that denominator is what we call the partition function. And that's super important. Okay, the denominator of a probability distribution function is called the partition function. And we'll spend the next several lectures computing the partition function for translational motion. There's a different kind of partition function for rotational motion, a different one for vibrational motion. So you're going to be wondering over the next week and a half or so, it's like, wow, we keep talking about this partition function. I've forgotten what that is. Well, just think about the word partition. It's like we've got these energy levels. How are they grouped? Well, they're grouped in translation, rotation, vibration, electronic. And we calculate different partition functions for each of those types of groups. Okay. And that helps us normalize the denominator so that we can know what our true probabilities are. So we're looking for probabilities, and we spend a lot of our time in the denominator trying to figure out what are the total possible numbers of energy levels. And then we could calculate accurate probabilities, because probabilities are going to feed into the amount of energy we have in the system, the amount of enthalpy, entropy, all of these different things. And eventually we're going to compare probabilities of reactants and products and get equilibrium constants. So in order to do probabilities, we have to have an accurate denominator. And in order to get that, we need these partition functions. So that's sort of setting the stage for what we're doing over the next couple of weeks. Now, sometimes you see this Boltzmann factor written as there's a beta in here, and I don't want you to be confused by that. Beta is 1 over kT. Okay, so that's just, if you're looking at the text or you're looking online, you'll see e to the minus beta epsilon, and you'll say, wait, I don't remember that, or I don't recognize that equation. It's the same equation as what we're talking about. My daughter's name is Katie, and I always wanted her to get a ball cap with beta to the minus 1 on it. I just thought that would be so cool. People say, what's that? It's my name, you know. She didn't go for it. Missed opportunity. All right, so the probability of any particular configuration is this, you know, Boltzmann factor for that particular state of interest divided by the partition function. And it seems pretty simple, but it satisfies all those constraints that we have on equilibrium, and that partition function is the normalization factor for this probability distribution. So let's look at some of the features of this Boltzmann distribution law. Now, I guess let's just go over the main sort of facts that govern our understanding of this thermal equilibrium. So every possible microstate of an isolated assembly of units occurs with equal probability. So this is saying, like in a p orbital, if we have a system like aluminum where we have that 3p electron, if those 3 orbitals are truly degenerate, then a microstate would be that electron being, say, in the px orbital. A different microstate would be in the py, and a different microstate would be the pz. And it's saying that that you have a mole of those molecules, or those atoms, aluminum atoms, that you're going to have a third. That a third of those electrons are going to be in the px, a third will be in the py, and a third will be in the pz. Okay, so they're equal probable. Okay. Now, there's also going to be some configurations that if we like, let me try to think of how to put this together. There's also going to be some other kinds of P1 configurations, right? An excited state would be that P electron being in the 4P, okay? But the dominant one is going to be the one with the highest probability. And it's going to be a higher probability that that electron be in the 3P because of energetic concerns. And so we won't really detect any of the 4p aluminums. Now, adjacent configurations of microstates are insignificantly different from the dominant configuration. Let's just think in terms of flipping coins. You know, if you flip a coin 100 times, or let's say 50 coin flips, 25% of those, you know, would be tails or heads, a 50-50 split. That would be the most dominant configuration. Now, they wouldn't be in order. You wouldn't get 25 tails and then 25 heads. That would be very improbable. But if you flipped it 50 times and looked at it, you would say, well, it's most probable that I have 25 and 25, but it's almost equally probable that I would have 24 and 26, right? Because they're not that different. Okay. So those would be called adjacent configurations. Notice, let's think about coin flips too. Notice how when we talk about a configuration, it's like we're summing up the categories of heads or tails. And so we're saying 24 tails and 26 heads is a configuration. A microstate would be the exact order. And so think about how many different microstates there are. How many different ways you could get 24 heads and 26 tails. A whole bunch of different ways to get that. But the configuration is that 24 to 26 ratio. Now, observations of the macroscopic properties of the system will be governed by this dominant configuration. And so the dominant configuration will be 50-50, or 50%, or 25 heads, 25 tails. And that would appear to be unchanging. Let's say this system is, you know, when you're sampling it. So you take a measurement, a chemical measurement, and it's like you did the experiment again. It's like you flipped the coins 50 times and you got another measurement, and you could look at it and you could say, well, it's that peak is just seems like it's stuck on 25 heads and 25 tails. The width of that peak would capture the 24-26 or the 26-24, and all of those adjacent ones, and that would give you the width of that peak. But it would look like that peak is not moving when those heads and tails are constantly flipping. And so that's what it's saying. We're looking at the macroscopic properties of the system. It's dominated by that dominant configuration, centered right on 2525, and it appears to be unchanging, but these microstates are constantly flipping. And this apparently unchanging dominant configuration is what we call the equilibrium state, and it's described by the Boltzmann distribution law. Now, Boltzmann did all of the math like in the late 1700s, 1780 roughly, and he did this for velocities of molecules. Okay. I've got a copy of the paper if you want to look at it, but it's a pretty involved. It would take us probably a couple of weeks to get through the math. So these are the main bullet points that came out of that, specifically this last bullet point. And so, think about gas molecules in this room. Their average velocity is going to be governed by the temperature, this Boltzmann distribution law. But, a fast molecule hits two slower molecules, and now it slows down, and the other two come back up to a faster speed. So they're constantly exchanging energy. So the system's changing constantly. Those would be the microstates. If you took a snapshot and said, okay, how much velocity did you have? And did you have? You'd have a set of velocities in the room. Then you let it go again. They're all going to change velocities. But the average will be related to the temperature governed by the Boltzmann distribution law. So let's look at these temperature effects. And so let's do an attendance check in Top Hat. So this is how we do attendance checks. This is the first one I've done. So let's go over here and create attendance. And so this pops up a little thing. And so enter this code into the Top Hat app. Can y'all see it? I don't know what y'all see on your end. Just a couple. Is anybody having trouble getting in? Is that okay? I can write the code on the board too, and we can go on. Oh, we got one more. Okay.
Does anyone want to?
Yeah. Is this? Okay, so I wonder where the 20th is. Okay. We'll see. All right, I'll call it finished. We're good. Do what? Yeah, that's right. Okay. All right, so back in. All right, so now we're going to actually do the problems. So you'll see in the notes handout that it's already worked out for you with the numbers, but that's just sort of check ourselves. And so let's do it by hand. Pretend you don't see that, and we'll do it from scratch. So you can get a scratch piece of paper, and I'll show you how I like to do these problems. Part of learning these problems is learning what is meant by all the text in the problem. So you're dealing with word problems, you've got to be able to parse out what's being asked in the problem. So this is a classic two-state problem. This is such a classic problem in PChem that a lot of times it shows up on the GRE, like the chemistry test for the GRE. And so if you take the discipline-specific test, say if you're going to go to grad school, it's probably an 85% chance that you'll have a two-level problem on there. Okay, it's so common. So what would be an example of a two-state system? Well, this could be, again, that vibrational energy for iodine. What's the probability of the iodine molecule being excited to the first vibrational state from the V equals 0 to the V equals 1? So that's an example of a two-level system. Of course, it also has one at 400 and one at 600 and so on. So it's an equal ladder of states. So it's not exactly a two-level system, but if you're at cold temperatures and you want to just treat it like a two-level system, you could do that. Another classic two-level system would be dissociation. So if you have bond dissociation and you want to know what percentage of the molecules would be likely to dissociate at this temperature, so you start cranking the temperature up and you're worried about your molecule falling apart, like a decomposition temperature, you could calculate this using a two-level system. Okay. So what are the population probabilities of a two-state system with an energy spacing of 200 wave numbers at room temperature? So you've got to understand all the different parts. So a two-state system is nice. We just have two quantum states that we have to deal with. You have a ground state and an excited state. And it typically will tell you some sort of information about the energy spacing. Now, in this case, it's in wave numbers. It could be in joules. Sometimes it's in temperature. Okay, and so we'll deal with that one later. Now, this is convenient because essentially KT at room temperature, so 298 Kelvin, is 298 Kelvin times that Boltzmann factor in wave numbers per Kelvin, 0.695. That gives us a thermal bath of 207 wave numbers. So that's roughly equal to 200 wave numbers. What do I mean by that thermal bath? Well, think about our energy level system. So we have the quantum state spacing of 200 wave numbers, and we also have the energy in the room that is this 200 wave numbers. So this is what I mean by a thermal bath. If the energy level diagram is a bathtub and the room temperature fills it up to about 200 wave numbers, we know we're going to have some excited molecules because we have plenty of energy to excite that molecule to the first excited state. You see the energy level in our system is 200 wave numbers and our thermal bath is 200 wave numbers. Okay. What if our thermal bath, what if this was at, 10 Kelvin? Okay, well, 10 times 0.695 would be roughly, 7 Kelvin. So, or 7 wave numbers. And so our thermal bath would be about 7 wave numbers. And our first excited state is 200 wave numbers. Probably not going to have any molecules in the excited state or any of our particles in the excited state. So this is this ratio that we're taking in the Boltzmann distribution here. See? And so let's go ahead and set up our energy levels. So we have our energy levels here. So we'll go, we'll do the 0 wave numbers on top and 200 wave numbers on bottom. I can put the i's here too, so I equals, do y'all like to start with 1 or 0? It doesn't really matter. 0, okay, 0 and 1. So that's our, okay, let's go ahead and do G of I, our degeneracies. There's 1 and 1. You see they're both singly degenerate. Let's, just for grins, let's do this ratio, right? We have e to the I over KT. All right, KT is 207 wave numbers. We can go ahead and make it 200, and our energy levels are 200. So here we have the energy level of 0 over 200. So that's equal to 0. And here we have 200 over 200. Will it help if I leave the 7 in there so you know which one's which? Okay, roughly equal to 1. All right. Let me go ahead and erase that 0 there. Notice I'm using the PowerPoint instead of the top hat annotation because top hat annotation is very irritating to me. Okay. So then we take the Boltzmann factor. So G of I e to the minus epsilon over KT. We have all the pieces we need. We just need to do that exponential. So we have 1 times e to the minus 0 and 1 times e to the minus 1. Thank you for that. So anything raised to the 0 power is 1, so we have 1 right there. And then e to the minus 1, somebody can do that. 0.36? 0.3? Let's do 2 decimals if we can.
It's 0.367.
Okay, so let's go 0.37. How about that? 0.37. Okay, so we've calculated our Boltzmann factors, but they're not probabilities, but they are relative probabilities. So notice if the ground state is 1, what's the relative probability that will be in the excited state? 37% if the ground state's 1. So these are relative probabilities, but let's normalize them. And how do we normalize any given event? We divide it by the total number of events. Here we have 2 events, and so that's what this partition function is. See the sum here? So all we have to do is just say Q is equal to this column summed. So 1.37. So we've calculated our partition function. So however many rows you have, if it's a 3-level system, you calculate each row, and then the Q is just the sum of that column. Does that make sense? It's all the possibilities added together. Now we can do our normalized probabilities. And so the normalized probabilities are the G e to the minus EI over KT divided by Q. And so this is pretty simple. This is this piece right here, 1 over 1.37. And this is 0.37 divided by 1.37.
First one should be 0.73.
0.73. Okay.
And then 0.27.
Okay, so we have a 27% chance of being in that state and a 73% chance of being in that state. And this is a nice thing because you can always check your work. So does this sum to 1? Yeah, it sums to 1. Okay. And so all your percentages, that's the way you can kind of check yourself at the end. All your percentages should add up to 1. And so this is our chance with the thermal bath being at roughly 200 wave numbers. We have a 27% chance of being in the excited state, 73% chance of being in the ground state. Okay. And just to check what I said, can someone take 27 and divide by 73? So 27 divided by 73. Yeah, 0.37. And so when I said that factor right here was the relative probability, so the probability relative to the ground state, that's true. So the 27% chance is the normalized probability of being in the ground state. But if you said for every 100 molecules in the ground state, I have 37 in the excited state, that's that relative probability. And a lot of times, if the system's really complex, that's an easier calculation. Okay. So that's the Boltzmann distribution. If we came into this system and we said that we're at room temperature and we did a spectroscopic measurement of iodine and we noticed that half the molecules were excited and instead of 27%, our conclusion wouldn't be that the Boltzmann distribution is wrong. Our conclusion would be that that sample of iodine is not at thermal equilibrium. So this percentage defines what thermal equilibrium is. Okay. And so what we would do to sort of prove that to ourselves is wait. Okay, and we would notice that it drops from 50 to 40, until it gets to this 27 to 73% ratio, and then we would say, okay, now it's at thermal equilibrium, and that might take quite a while, depending on the system. Okay. It might not take long at all. It just again depends on the system and how dynamic it is. Any questions about this? So there's a lot of these little calculations, the things that you can do on the homework and so on. So here's to check our work. We did slightly different, but it's because of that 0.38 instead of 0.37, but essentially the same calculations. Okay, now let's change the degeneracy. So just to reinforce it, let's do it again, okay? I, 0, 1. So the only thing that changes in this whole table, well, at least in the inputs of this table, are the degeneracy factors. And so here now we have G of I is 1 for the ground state and 2 for the excited state. So the individual Boltzmann factors, are going to be 1 times e to the minus 0, which is equal to 1 again. And now we have 2 times that 0.37 from last time. Okay, so equal to point, what is that, 74? Yeah. So now since our degeneracy of the upper state is 2, we have more chairs. And so what does our partition function show? It shows a larger number. So this is something that you can, what do I want to say? This is a principle that you can hold on to, that the partition function is a measure of all of the accessible states. It's roughly a measure of the accessible states. It's not an integer. It's not going to tell you there's 3 states to populate, because we don't have enough energy to populate all of those states at equal probability, right? So it's not 3. It's going to be less than 3, but it's not 0 or 1. In fact, its minimum value is going to be 1, and we can show that in a second. So it's going to be somewhere between 1 and 3. And it's capturing, again, sort of how many states are accessible at this temperature. It's saying, on average, 1.74 states are accessible. It's a measure of how many states are accessible at that temperature. Okay, let's do the probabilities. So this is 1 over 1.74, and this is 0.74 over 1.74. So someone with a calculator should hammer that out for me.
0.57.
On the top, 0.57?
Yes, sir.
Okay. Okay, and the bottom?
0.43.
0.43. Okay, now the one thing I need to point out is this degeneracy is the degeneracy for the whole excited state. Okay, and there's 2 of those. And so it's going to give us, if we take that 0.43 and divide by 2, what do we get? 21 and a half. Did I do that right? Yeah. So it's divided equally among those 2. So that's the 0.43 divided by 2. So we have 21.5% chance of being in each of those states. And then 57% chance of being in the ground state. Now think about this. It seems just so weird to me that we haven't changed the energy spacing at all. But just by putting 2 chairs in the excited state, we have more excited molecules. Go to the previous calculation. In the previous calculation, we only had 28%, 27% excited. All we did was add another chair at the excited state, and now we have 43% excited. Isn't that crazy? It's just totally statistical. But that's represented in nature. We see that. That just kind of blows my mind. I like to point that out because that's a head scratcher. More molecules are excited just because there's an opportunity there. And so when you add more degeneracy, you're going to have more molecules in the excited state just by adding more degeneracy. And in rotational systems, the degeneracy is, so J equals 0, J equals 1. The degeneracy is 2J plus 1. So when J equals 0, we have a single level. When J equals 1, we have 3. Okay, then 5. then 7, then 9. And so whenever we look at this, if we did absorption spectroscopy on this molecule, like we did the carbon monoxide, when we look at that spectrum, remember the peaks went like this? They got big for a while and then they came back down. They got big here, this right here, this slope was the 2j plus 1. So this was a measurement of the probability of the molecule being in the ground state. It was smaller than all these others. So it was really a small probability that the rotational molecules, the rotational excitation was going to be in the ground state. Why? That's the lowest energy state. That's the one favored by the Boltzmann distribution. But it was less probable than the excited states because of the degeneracy. There were more chairs in the excited state. So if you throw a mole of molecules, of carbon monoxide molecules at this rotational set of levels, it's more likely, it's all about probabilities, it's more likely they're going to be in the excited state because there's more chairs there. There's only one chair in the ground state, but there's a whole bunch of chairs in the excited states. And so you would say, well, it's just going to be in the excited state. You know, what's the limit? Well, the limit then is the amount of energy you have, the thermal bath. So this drops off because of the Boltzmann factor. So this Boltzmann factor here is what causes it to drop off, and that's the temperature effect. So the degeneracy is temperature independent, but the population of the excited states as they go higher and higher in energy is related to that thermal bath. So if we were to cool this thing down to absolute 0, okay, so our temperature would be 0. Let's see. Yeah, okay, so let's get close to 0. Let's go like to 1 Kelvin, okay? And so this guy right here is really a small denominator. But at the ground state, the energy is 0. And so this is still going to be 1. But right here, this factor, if we have e to the minus 200 over K times 0.001 Kelvin. Let's go really cold, all right? A millikelvin. That is such a tiny little number in the denominator that this factor, this ratio is going to be huge, okay? And I have an e to the minus huge. So if we plot this out, okay, if this is x and this is e to the x, e to the minus x, okay, then it's going to be really small. And so this piece will essentially be 0. So as, let's see if I can write this in here, as t goes down, e to the minus e over kt goes down. And so what that means is that there's almost no probability of being in an excited state. So if this were 0 here instead of 0.74, what would our partition function be? Nothing changes this piece because the energy is equal to 0. So we're always going to have e to the minus 0 for the ground state. Yeah, and so this piece is going to be 1. This thing's going to get really small and eventually sort of approach 0. And so then our partition function is 1. And you can see at really low temperatures, our partition function goes to 1, which means we have one level to populate. We have one partition, and it's the ground state. We have only one place to go at really cold temperatures. And so if this were the rotational spectrum and we cooled it down, this Boltzmann factor piece would drop off right there. And so we would have a degeneracy piece going up, and we'd have a Boltzmann piece going down, and we would have only one peak, and it would be all the molecules in the ground state. If we have a really high temperature, then the Boltzmann factor doesn't drop off till way over here, and we're going to have many more peaks. And so at high temperature, our partition function goes up. We have more options. We can populate excited states. And then at really cold temperatures, everything collapses down and we just have one peak. Okay. So what, and we should have seen that, when we did the numerical Schrodinger equation in the last semester, when you're playing with the temperatures, you should see that, as the temperature goes down, we only have one peak available at ground state to the first excited state, the fundamental, essentially, no hot bands. So I keep bringing back spectroscopy because that's how we probe these things. So what we did last semester with all the quantum states and determining why these energy levels are where they are, that's sort of done with, but the thermal equilibrium of those thermal equilibrium of those quantum states is what we're talking about now. And how do we know that that's the way it occurs, and that is through spectroscopy. So we wouldn't know anything about these quantum systems without spectroscopy. It's a way to probe the system without getting in there with tweezers and things like that really interfere with the system. Okay. Now we can do this an interesting way. We can do this in reverse. So what is the temperature? What temperature in this system would yield a 50% probability for the ground state? So notice the last part, we had a 57% probability of being in the ground state. So this was at room temperature. We had a 57% chance of being in the ground state. So do you think the temperature would be higher or lower to get that to 50%?
Lower.
So remember, we're talking about the probability of being in the ground state, and it's at 57 right now at room temperature. So if we lower the temperature, what's the probability of being in the ground state? It'd be higher, right? So we go to 58, 59, 60. So then if we raise the temperature, we're going to have more excited state molecules, so that probability of being in the ground state would drop. Okay, so it should be higher temperature. So just, again, that's the kind of sort of think, all right, I'm going to do this problem. What do I expect out of it? So try to think your way through. It's probably going to be higher than room temperature if room temperature gave us 57%. So how do we set this problem up? Okay. So the probability, okay, so we want the probability of being in state 1. Okay, what is that probability? That probability is the degeneracy factor of state 1, e to the minus 200 over kt. And let's go ahead and write everything out. G0 e to the minus 0 plus G1 e to the minus 200 over kt. So can everybody agree that that's our probability for being in the let's see, did I do the ground? Oh, I want to do the ground state. Okay, I'm sorry. So this is going to be a 0 here. Okay. And that's going to be a 0 there. It's ground state probability that we're doing. Okay. So this is the state of interest on top, and this is all the states on bottom. Okay. And this probability, we want that, and this is going to be 0. We want the probability ground state to be 0.5. So you see the temperature here is really irrelevant because we've got this 0 on top, so we can ignore that piece. And so we've got temperature buried down in here. Everything else we know. The ground state, the degeneracy for the ground state is 1. The degeneracy for the upper state is a 2. And so we know all of our factors. It's just a messy problem. We can start rearranging things. Okay. And so then we have 0.50 times, and this is a 1, so this piece is equal to 1. 1 plus 2 times e minus 200 over kt. And that's equal to this top piece. What is that? That's going to be 1 also, is equal to 1. So that's our problem simplified a little bit more. Let's multiply the 0.5 through. And so we have 0.50 0.5 times 2 is going to get rid of the 2. We have e to the minus 200 over kt is equal to 1. Now I could subtract that 0.5 from the right, and so we would say e to the minus 200 over kt is equal to 0.5. Somebody follow that so far? Okay. And now we can take the natural log of both sides to get rid of the exponential. Okay. So we have minus 200. Wait, I'll go ahead and do wave numbers here. Over kt is equal to the natural log of 0.5. Let's see, we need to swap some things around, and so we'll have on bottom 0.695 wave numbers, Kelvin, and it's Kelvin to the minus 1 times the natural log of 0.5 is equal to temperature. You see how I swapped those two? I multiplied both sides by temperature and divided both sides by the natural log. I don't know why I have that extra parenthesis. And we're ready to hammer away with our calculator now. It looks like we're going to get a negative temperature, but this natural log of something less than 1 is going to be negative 2, so that's going to be convenient. So that'll kill our negative sign. What'd you end up with? Anybody? 415? Okay, 415 Kelvin. All right. So higher the room temperature, right? Room temperature is roughly 300 Kelvin. This is another 115 Kelvin higher, and that's going to give us an exact 50% chance. So we would have 50 and 25 and 25 at a higher temperature. Now, we're out of time, so we can just guess at this last one. How could I get it to be 33, 33, 33? In other words, equipartition, right? Everything has the same probability. Really high temperature. So that this 200 wave number difference is irrelevant. It's as if all three energy levels are the same energy compared to the thermal bath. When you really raise the temperature, 1,000, 2,000 degrees Kelvin, it's going to be 33, 33, 33, and your partition function will be 3. Because you'll have 3 levels that you can populate, and all your probabilities will be this level over 3, that level over 3, that level over 3. Okay. All right, cool. That's Boltzmann distribution.